Hello everyone, how are you doing? All are doing good, I hope so. Welcome back to SMR Online Physics. I am Mahesh, your physics teacher. Today I'm going to discuss about refraction at spherical surfaces. Okay, if you are new to this channel, do not forget to subscribe my channel. Okay, let's enjoy physics. The topic for the day is refraction at spherical surfaces. So far in my previous classes I have been discussing about refraction in various possibilities, right? Okay, that's it. Refraction at spherical surfaces. We have spoken about refraction of light for two different transparent media happening at plane surfaces. Then we spoke about rectangular glass slabs. Then we spoke about triangular glass prisms. Then we spoke about critical angles and total internal reflection and its applications in day-to-day life. So today the question is, what if the surface is not plane but rather curved? How will the refraction take place and what is the mathematical implication out of it? And later on, as we will progress forward, we will also see what is the use of learning the refraction at spherical surfaces. Right? Here we go. Let's imagine a surface, something like this. Curved surface. This is what I mean to say, a spherical surface. Alright. So, a line passing right through the midpoint of the spherical surface, which we'll use as a reference, basically called as the principal axis. But right now you'll see that what I'm trying to mean here is the surface behind this spherical surface is completely made up of a different transparent medium. Let us take the refractive index of this medium is N2, and just in front of it, this is a very different transparent medium. Let us take the refractive index is medium N1, right? So let us say this point is the midpoint. Let us call it as P. So what is going to happen like? Now this is the object, a point object for a reference. So how will the light refract as it passes from one transparent medium into another transparent medium? And the surface, the interface is a spherical one. Alright, so let's get started. So you know some basic facts. A ray of light goes and strikes over there at a certain point. Now students definitely have small but important doubts. How to draw a normal at this point? See, even though it's a spherical surface, our imagination will help us to think out that it can be minutely broken down into infinite plane surfaces. So at the point of incidence on this spherical surface, at this point I can minutely imagine it's a plane surface. So always imagine a tangent drawn at this plane surface. So the point where the tangent touches it, there you'll always find your normal. So normal by definition always is an imagined line passing right through the point of incidence and definitely connected to the center of curvature of this spherical surface. So here we go, we get the first distance, the center of curvature to the center of the spherical surface, that is P in the diagram. This distance is called radius of curvature. Clear? Okay, good. Now this ray of light should have gone straighter, but definitely won't go that way. Let us visualize the condition. Let me put the condition clear out here, that N2 is greater than N1. Great. So if N2 is greater than N1, definitely should bend towards the normal. So let us say it bends something like this. That's it. And here you get the image formation for this point object O. So let us name it out. Then let us call this point of incidence as M, and let us imagine a perpendicular from M onto the principal axis, and we are dealing with spherical surfaces with very smaller apertures. So this point P and this point Q are almost exactly close, very very close to each other. The distance PQ, please mind it, is almost like negligible distance. Alright, okay, here we go. So the angle between the normal and the incident ray is our angle of incidence. The angle between the normal and the refracted ray is our angle of refraction. That's it. Okay, so let me get some space to do the maths here. Let us create a relation between N1, N2, the radius of curvature, the distance of the object from the spherical surface. We all know it very well. This is the object distance denoted by alphabet U, and the distance from P to the image definitely is called as the image distance, popularly known to all the students, denoted by alphabet V. Are you feeling good about it? Okay, everything is very clear. Okay, let us get to the maths here. So by Snell's law, let me write it over here. By Snell's law, okay? If you haven't watched my previous videos on these topics, please go back and watch it all, okay? You'll definitely like it and enjoy physics. So by Snell's law, I can write this relation something like sine I by sine of R is equals to N2 by N1. Alright? So we can also cross multiply and check it out. N1 sine I should be equals to N2 sine R. My dear, now comes a very important approximation. That is, for very small apertures, we can say sine I is almost equal to I, and that in turn is also equal to tangent of I. Is only true for very very small angles, and similarly sine of R is also equal to R, very much equivalent to tangent of R, wherever you may need it like. Alright, so for smaller apertures this is always correct. Okay, so here we go, we have this relation, hence we can write N1 I should be equals to N2 R. All good. So let us see what is I there. So this is your I. Okay, let us leave this equation over here. So I, my dear, please observe closely, this I for this triangle OMC, for the triangle OMC, this I is your exterior angle. Am I clear? So it means that this remaining angle is 180 degrees minus I. Good. So it also means from geometry, this angle, that is angle MOP plus angle MCP, or you can call it as even Q, both will not mean anything different. These two angles, the sum of these two angles should be equal to I. Am I clear? So we'll get something like this. In triangle MOC, I get your point clear? Okay, so we can write I is equals to angle MOP plus angle MCP. That's pretty good there. Okay, and similarly now we will say search for another angle or the triangle here. This is your angle R known to you. So if you look into this and this, if this is another angle close by, if this is your angle, then this is definitely your 180 degrees minus this angle of C. Alright, so if you just check it out, angle R plus this angle of I plus 180 degree minus angle of C should be equal to 180. So hence you will find in triangle MCI, you'll find that angle MCP should be equal to angle R plus angle MIP. Yeah, all clear, I suppose, right? Okay, not at all confusing. It's very simple. Just keep on following it and you'll find that angle R is equals to angle MCP minus angle MIP. So you got your I's and you got your R. So there we go. In equation 1 I have the place for I and R, but I'm running out of space. Please excuse me. So let me just cut it down slightly there. Okay, right. So in equation 1, if I put it back there, what I will get, let me check it out. N1 I, this is angle MOP plus angle MCP should be equal to N2 multiplied with this angle R. Just put it out the values. Angle MCP minus angle MIP. Hope I am clear? Yeah, right. So let us see quickly what is there. Angle MOP. Angle MOP. Okay, right. So even if you take the tangent of this angle MOP, okay, even if you take the tangent of this angle MOP, tangent, as I already told you, the tangents and the sines will be almost equal to each other because of smaller apertures. So angle MOP can be written as MQ by OQ. Okay, you can say MQ by OQ, you could have said MP by OP. Please do not misunderstand, right? Angle MCP, this is the triangle I'm talking about, MCP. So I could have easily said is again MP, or you could have said MQ, whatever. Let me just change this out, okay? Let us call this as MP so you don't have any sort of confusions. This is MP by CP. So quickly on the other side, angle MCP, where is the triangle MCP? Again you find the same thing coming up, MP by CP minus angle MIP. So this is MP by IP. Alright, I hope I'm not confusing you. Anyone? We are enjoying there. So let us quickly see what is what. MP. This is MP, 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 MP. Lots of MPs all fly away in air. You're left with 1 by OQ plus 1 by CP equals N2 into 1 by CP minus 1 by IP. All MPs have got disappeared, right? I don't want my equations to get disappeared for sure, so I need some more space. If you all excuse me, if you have noted it down, yeah, I can rub this off and get my space. All right, that's it. I rub this off, small board, excuse me, early days. I hope you understand, right? So we'll get N1 into this. Let us quickly put in there OQ, or you say OP. Okay, good. This is your sign convention all on the left hand side, so I put a minus there. Sign convention which we applied for spherical mirrors remain the same, left of the P. 1 by CP, where is the CP? CP is your radius of curvature, so I put it as 1 by capital R is equal to N2 multiplied by 1 by CP, the same thing, 1 by positive R minus 1 by IP. So again on the right side, so not an issue at all. Let us not disturb our equations. I get rid of that old matter. Okay, right. So what we have right now is minus N1 by U plus N1 by R is N2 by R minus N2 by V. Just we rearrange the equations, my dear. Keep patience and you'll get everything right. You get N2 by V minus N1 by U equals N2 by R minus N1 by R. So I write the final equation. What we have been waiting for is this. N2 by image distance minus N1 by object distance is equals to N2. Sorry, let us not write that way. 1 by R into N2 minus N1. There we go. This is a beautiful equation for refraction at spherical surfaces. N2 by image distance minus N1 by object distance equals 1 by the radius of curvature of the spherical surface multiplied with N2 minus N1. So now I'm going to discuss about lateral magnification at the spherical refracting surfaces. Okay? So I'm very sure the students have heard about this term called lateral magnification, also called as transverse magnification, defined as the ratio of the height of the image to the height of the object, okay, at spherical surfaces. So get ready for a beautiful derivation of this expression. How can you express the lateral magnification in terms of the refractive indices of the medium and the object distance and the image distance? You're going to get a beautiful relation. So let's get on to that. Why to waste any time? This is our refracting surface, which is spherical in nature, and this is your reference line, the principal axis. This is the midpoint P. So make it very sure that you're clear in your head. Anything beyond this surface has a different refractive index. Let me name it over here. This is something like N2. This is like something N1, where N2 is greater than N1. So let us derive this expression for an extended object, something like this. So this is our object AB, right? So let us choose a ray of light which is incident normally on the refracting surface. So let us say this is the ray, and here we go. So this has to pass through the center of curvature because it's a case of normal incidence. Right, it passes through, hence the tip of the object's head, A, the image is formed over here. This is called A dash, this is your B dash. That's it. Very easy to identify. What is easy to identify? That this distance from P to B is our object distance U. What is easy to identify is distance from P to C is called the radius of curvature of the refracting surface, and the distance measured from P to the image is very appropriately called as the image distance V. Is that clear? Alright, let us get on to that thing. This is your 90 degrees, this is your 90 degrees. These two angles are absolutely equal to each other. So those two triangles, what you can see, are definitely similar to each other. So by definition, we know that magnification can be written as the negative of A dash B dash by AB. Why negative? Because that is your sign convention. Any distance measured perpendicular and below the principal axis is minus. That's your negative y-axis. Anything above the principal axis is your positive y. So there's a positive sign. Alright, since triangle ABC and triangle A prime B prime C are similar triangles, okay, from geometry, so we can definitely write M equals minus A prime B prime by AB, which can be easily replaced as minus A prime B prime, observe the diagram closely, can be replaced as B prime C and this by BC. So hence you can write M is equal to minus I will do some geometrical techniques. B prime C कैसे लिख सकते हैं बताओ? How can we write that? We can definitely write it as PB prime minus the PC. PB prime से PC हटाओ. You are left with B prime C, and BC को कैसे लिख सकते हैं? You can write with PB के साथ PC को जोड़ दो. Plus PC, okay? Is that good? Now let us replace what we know. Minus over there. Then we put a bracket. What is PB prime? Right side. So no problems. It's plus V. This is minus. What is this PC? This is on the again right side. This is your R. सब ठीक है ना? बढ़िया? Okay, good. PB देख ले फटाक से. ये हो गया minus U. संभाल के because it's on the left hand side, and PC is on the right hand side. So ये हमारा हो गया plus. So M बन के आता है. What do we get for M here? This minus is there. So you'll be left with R minus V. यहाँ पे गड़बड़ ना करें. ये R minus U होगा. ठीक है? So this is our equation number 1. So what is the purpose and what exactly are we doing here? Now I'm trying to find an expression for this M, and this is where I got stuck right now. So I need to find out what is that R for from this equation. R कैसे पता करें? Yes, the first part of this class. What do you got? क्या मिला था वहाँ पे? ये बहुत ही सुंदर सा equation मिला था. We got it. We know लिखते हैं. क्या लिखे थे भाई? कुछ याद आ रहा है सभी को? N2 by V. N2 by V minus N1 by U is equal to 1 by R into N2 minus N1. Check कर लें. Did we write it correctly? Definitely yes. So यहाँ से R निकालते फटक से. V U LCM बन गया. ये हो गया N2V. Sorry, ये गड़बड़ होने वाला था. This is N2U boy. This is U गया. So you are left with N1V. So this is equals to 1 by R into N2 minus N1. All good now? Keep checking up. So you find R comes up, and definitely you can see that this entire thing is going to go down, and then again inversion. Also काफी common है. N2 minus N1 into VU by N2U minus N1V. This is where we again get stuck up, okay? Right. So now I'm going to put this R in this equation, and let us find out what is R minus V and what is R minus U. Quickly, I need some space, so I rub this off. ठीक है? Okay, right. So therefore, I did not rub this off. I need that equation. Therefore, R minus V फटक से बनाते हैं. R is this. It's a big thing there. N2 minus N1 into UV by N2U minus N1V minus V. So you end up getting all these things. N2U minus N1V. If you suddenly end up coming into this class and write it somewhere in the middle, you will be getting stuck. Okay? डर जाओगे बेकार में. So definitely watch it right from the beginning. And this is this entire thing going up there. Multiply it carefully. N2UV minus into minus is plus. N1V square. सब कुछ ठीक है. N2UV minus or plus. ये उड़ गया. And you're left with N1V as common there. This is V minus U on the top. N2U minus N1V. Most of you can do it by yourself. Now let us find out what is R minus U. I need some space, so I get rid of all these things. I'm sure that you have noted it down in your copies. You're doing it well. All right. Okay, good. So similarly, and R minus U, फटक से निकालते हैं. This is your R now. Luckily, that entire thing is right there. UV by N2U minus N1V minus U. Okay, this minus and pluses That is, the sign conventions play a very major role in ray optics. So what I have is N2U minus N1V. This is N2UV minus N1UV minus this entire thing. You're going to get N2U square minus into minus is plus N1UV. We are looking for some cancellations. N1UV आ गया, मिल गया, ये गया. Can you see it here? Can you see it here? Can I write this one step right there? Maybe slightly risky. So let us write it over here quickly. So R minus U comes out to be N2U, you know, N2U. N2U is common. Can you see it? Okay, I'm jamming up. N2U is equals to V minus U by N2U minus N1V. So that's it. That's your R minus U. This is your R minus V. These two equations we need, okay? Please note it down, those who are doing it. You can pause it and definitely do it. I need some space, so I get rid of this expression out here. So finally, we are about to finish it off. Therefore, magnification M was R minus V by R minus U. Put in these expressions out here. N1V on the top. This is V minus U by N2U minus N1V. So that comes down, that goes up. ये ऊपर चला जाएगा, so N2U minus N1V, and this comes down, N2U into V minus U. So now I can definitely clear this off. This is what you're left without. So hence M is equals to, this entire expression is blown off. Yeah. This is also out, and hence you're left beautifully N1, the refractive index of the first medium multiplied by the image distance by refractive index of the second medium multiplied by the object distance. This is another beautiful relation you learned from today's class on SMR Online Physics. If you definitely like this video, do like it and share it to the needful students, my dear. Share it to the needful students. And if you're new to this channel, please do not forget to subscribe my channel. See you back again on SMR Online Physics. Thank you. Have a great day. Bye-bye.